Hi, my name is Shawn McAllister. In this video, we're going to talk about the scaling of IT systems and how the methods for scaling applications don't work as well when scaling the messaging system that underpins them. Here you see a system architecture where external users connected to a JMS message broker access services provided by the platform. Example service users could be web servers converting browser interactions to internal service requests over JMS, or could be web service gateways in a B2B application. When an application can't keep up with the number of requests it's getting, you can increase application capacity by adding a new instance. This scale-out approach is called horizontal scaling. Instances of applications run independently enough that you can increase performance linearly as you add more application instances. That means 5 times as many applications can process 5 times as many requests. But what happens when the rate of external requests exceeds the capacity of the JMS broker that connects users to those applications? That is the main topic of this video. Let's now look at a typical enterprise service bus, or ESB. Here we show 4 applications, each with multiple instances, accessed either directly by service users or by internal applications in a service-oriented architecture approach. There can be different numbers of instances for each application depending on transaction processing rates per application and demands for these transactions. In this example, there are more instances of the inventory system than there are of the order fulfillment system. Let's also assume that the JMS message broker can handle 1,000 messages per second in as its maximum rate and 1,000 messages per second out as its maximum rate. As in the previous discussion, if you need to add more processing capacity for a given application, you add more instances and you get linear scalability. But now let's go back to the situation where the messaging demand exceeds the capacity of the message broker. And how do you scale your messaging layer? You could horizontally scale the entire system and duplicate the whole infrastructure to double your capacity. That's rarely done due to the cost and complexity of such an approach. Imagine the scale of this as you go to 4 or 6 or tens of brokers. You typically have applications that you don't need to replicate for various reasons. For example, applications that only need to scale based on average load and not peak load, or applications that are rarely accessed or whose cost to replicate them make it prohibitive to scale in this way. In our example, this is the case for the 3 applications shown in orange here. What you really want to do is to not duplicate those types of applications and instead access a shared pool of them from anywhere in your system. This is a much more cost-effective and manageable way to scale the system. But there are issues when you do this. Let's say, for example, you have an external application connected to JMS broker A that needs to access the services of the shopping cart, which is connected to JMS broker B. That interaction would look something like this. In this case, the message entering broker A must be sent to broker B for service by the shopping cart application, and the reply returned from broker B to broker A, where the requester is connected. Likewise, if the inventory system needs to interact with the order fulfillment system, then messages need to flow from broker A to broker B and then back. What this means is that there is a need for messages to flow between the JMS brokers to allow users and applications on one broker to interact with the users and applications on the other broker in an any-to-any manner. Now let's say that as a result of this, you end up needing 300 messages per second of volume to be exchanged between both broker A and broker B in each direction. Now, since each broker has an aggregate input capacity of 1,000 messages per second, if 300 of those come from the mate broker, that means that the input rate from external users is now no longer 1,000 messages per second, but is 700 messages per second. The result is that the combined input rate of the system from external users is not really 2,000 messages per second, but only 1,400 messages per second. And that means that 2 times the amount of messaging infrastructure only provides 1.4 times increase in total external capacity. And this is due to inter-messenger broker traffic or leakage. Now let's look at 3 additional issues when you scale from 2 brokers to only 4. The first issue is diminishing returns. In this case, I show the interbroker traffic as remaining at an aggregate of 300 messages per second to and from each broker, but typically the amount of interbroker traffic increases as you add more brokers. Specifically, the likelihood that a request from an application on broker A will also be serviced by an application connected to broker A decreases as you add more brokers. As the amount of interbroker traffic increases, the amount of external request traffic that a broker can service decreases, which further decreases efficiency. The second issue is focused overload. Because it's difficult to understand and predict all the communication patterns between the applications and perfectly balance applications on all brokers, you can end up in situations where the demands on a particular broker exceed its capacity. In this example, a total demand of 1600 messages per second is placed on broker A, but because its capacity is only 1000 messages per second, broker A is overloaded. This bottleneck results in degraded system performance and causes broker A to be a slow consumer to each of the other brokers, which in turn can impact their performance. And we'll talk more about slow consumers in another video. Now, to avoid this, typically people engineer their message brokers with lots of excess capacity in order to deal with such bursts. But doing this results in the third issue, stranded capacity. Stranded capacity is when you have capacity on one or more brokers that you can't make use of. Often this excess capacity will never be used, but you don't know that because you can't predict the traffic patterns. Sometimes it's planned to be there to absorb bursts of activity that do in fact happen, and this is fine, except you can only use the capacity on broker C to deal with the load targeted at broker C. You can't use the capacity from the other brokers. This means that if broker A is in focused overload, the excess capacity of the other brokers is stranded and can't be brought to bear to address this problem. You have sluggish system performance, even though you're paying a lot for the capacity that you have in your system. It's just that the capacity is in the wrong place. All this complexity and waste results from the horizontal scaling, which was necessary because your single broker didn't provide enough performance. What you really want is a single message broker that can deliver a lot more performance. If you had a single broker that was able to handle 4,000 messages per second, that would be far better than 4 message brokers handling only 2,800 messages per second from external users. With this single broker, you would have no interbroker communications, which not only means a higher usable message rate, but also means no focused overload and no stranded capacity because there's no partitioning of your message processing. And that's all well and good, but a lot of people need even more than 4,000 messages per second in their messaging system. So what if you had a technology that supported 200,000 messages per second in a single broker? That is what Solace messaging appliances provide. For many applications, this means that horizontal scaling of the messaging layer is not required at all. Now sure, if you need more than 200,000 messages per second, you can horizontally scale a Solace deployment by adding more appliances, but scaling in units of 200,000 messages per second is far simpler than scaling in units of 1,000 messages per second. And this brings me to my last point, vertical scalability. With software message brokers, your only option to increase performance is to horizontally scale by adding more brokers. As mentioned previously, you can do this with Solace appliances as well, but with Solace technology, you can also increase the performance of your existing appliance just by upgrading to faster messaging cards. This type of scale-up capability is called vertical scalability. The black line at the bottom of this graph shows the maximum message rate in production of a popular enterprise message broker. The blue line shows the performance of Solace's entry-level persistence card, the ADB2. This card already provides well over 10 times the message rate of software brokers, and that's what allows you to avoid considerable horizontal scaling. If you were to start with this card, and then you need to increase performance later, no problem. You just upgrade the ADB2 in your existing appliance to an ADB3 card whose performance is shown by the orange line, and you get more capacity in the same footprint. You don't add additional appliances, and there's no impact to the architecture or implementation of any of your existing applications. Today we contrasted horizontal scalability when applied to applications with its results when applied at the messaging layer. Increasing capacity by adding more message brokers is inefficient due to the unavoidable interbroker traffic or leakage and produces diminishing returns as you add more brokers. More message brokers not only results in more complex operational environment, but the traffic management complexity also leads to focused overload and stranded capacity problems. Having a messaging technology that can handle huge message rates in a single broker or appliance, in Solace's case, overcomes all these problems and results in no interbroker inefficiencies, no focused overload, and no stranded capacity. With fewer but higher performance message brokers, the operational environment is much simpler due to fewer moving pieces, application architectures are simpler, and the overall performance of your system is more robust and predictable.